So I'd like to explain first what a semiconductor nanocrystal is. Imagine that you can look inside a crystal with such a powerful microscope that you could count every atom. And now imagine a crystal so tiny that you could actually count every one of the atoms in it. Maybe it would be 10 on a side. That would mean a total of only 1,000 atoms. When a crystal is that small, it behaves completely differently than normal matter that we hold in our hands and can see with our eyes. Here's an example of a very fundamental property that's very different. Have you ever been to a science museum where they have one of those large funnel shapes and a ball starts rolling around the top, and at first it's kind of moving slowly, and then as it starts to move down the funnel, it speeds up and gets faster and faster? Well, think of a crystal that's so small as being a part of that funnel that's really tiny, and inside it, if there's an electron in there, it zings around really fast. That tiny electron then can emit light, and the color of light that it emits will depend on the size. If it's a little bit smaller, the energy of the light will be higher, so it will be bluer light. And in this way, you can use nanocrystals to make materials that emit the full rainbow of colors. Such a large rainbow that you can reconstruct with it every color that you see in nature around you. And that's a technology that's used, for example, today in quantum dot televisions or QLEDs. The challenge of climate change is one of the greatest challenges facing humanity. And part of that challenge is to learn how to make new materials that can harvest the energy of the sun and put it to beneficial use with as few losses as possible, but also to do it on a vast scale. It turns out that nanomaterials can be made in extremely high quality, but at relatively low cost. And they can be used to absorb light from the sun. And when crystals are different size, they'll absorb that light without losing it to thermal energy or heat, which allows more efficient conversion to electricity. So Michael Grätzel has already shown some uses of nanomaterials in solar energy, but there will be many more over the years that will come from nanomaterials being used to harvest solar energy for electricity, but also potentially to simulate or emulate photosynthesis to make chemicals, and possibly even to make new kinds of solar harvesting materials. So I'd like to describe some of the applications that semiconductor nanocrystals have already had. They can be used inside displays. So in a color display, there's always a red, a blue, and a green color that can be excited. And those colors interact inside your eye, mixtures of them, to reproduce all the colors that we can see around us. When we put quantum dots into a television to produce the red, greens, and blues, the size of the particle can be used to precisely tune the color to match the best spot in energy that matches the receptors in your eye. So the red, greens, and blues are extremely pure colors, and when those are mixed, they can recreate the full spectrum. So that's an example which enables, for example, artists and photographers to achieve better color reproduction, but it also results in very, very high efficiency for those displays. which means that they consume less energy and they can be used in a variety of new applications. Looking into the future, there could be some really interesting new applications that will emerge. The foundational work that Michael and that I have worked on, along with colleagues from around the world, have opened a door to potentially really interesting future work. One is to try to emulate the process of artificial photosynthesis. That would mean to make materials in the lab that absorb light and then convert that energy into chemical energy, to store the energy in molecules. So, for example, instead of having a solar cell where it makes electricity and the only way to store the electricity is with a battery, maybe one day we could make a fuel, a chemical fuel, which then could store the energy for any amount of time to be released when we want to use it. And that would, in a sense, complete an artificial human carbon cycle that would allow us to emulate what plants do. A second, more far-out application, but one that we're very excited about in my lab right now, is actually to make a funny kind of refrigerator. Perhaps you're familiar that in a refrigerator, gases expand and contract, and that expansion and contraction is what's used to either heat something up or to cool it. Imagine now a new kind of refrigerator which, instead of working with a gas that expands and contracts, instead actually works with photons, with light, and the light would be expanding and contracting in order to heat and cool objects. It's a very funny idea. People have thought about it for many decades, but the materials never had the possibility of being high enough quality until some recent developments in nanoscience, some of the materials that we and others have been making. So I foresee quite a long run of new applications of these materials.